Hello, welcome to Correlation Analysis. I'm Jessica with Splunk Education. In this module, you'll learn about transactions, sub-searches, and some commands you can use to analyze data from multiple sources. We'll be looking at data sources from the fictional company Buttercup Games. Let's begin by learning about transactions.
Events used to form a transaction can come from multiple data sources. As an example, events from a single online purchase can span across application, database, directory, email, and a host of other systems. Being able to combine these events into a single transaction builds a story of the journey the purchase took on our servers. The transaction command adds two fields to events: duration and event count. Duration is the time difference between the first and last event in a transaction. Event count is the number of events in the transaction. We can use definition options to specify the criteria used to determine how to group the events. These include starts with, ends with, max span, and max pause, to name a few. When we conduct a search in Splunk, results are returned in reverse chronological order by default. The transaction command depends on this reverse ordering to return correct results. If any commands in the search reorder events, make sure to sort the time field in reverse order before piping to the transaction command.
The transaction command allows you to group events together based on specified constraints. The transaction command groups together events that share the same value in one or more fields. The transaction command will create much larger events, which will be our transaction events that all share the same value in that field, and we can then apply additional options to the transaction command to control them based on what they start with and end with, control the overall time of our transactions, and we can also work with specific fields that are added in the sidebar when piping to the transaction command. Now, if multiple fields are specified within the transactions field list, events with common values in all or some of the fields are grouped into a single transaction. When adding more than one field to the field list in the transaction command, the transaction command will return events with the same value in both fields, the same value in one field or the other. Let's take a look at a couple examples. In this basic search, we're looking across the web index source type of access combined, and we can see we're getting events back. Some of these events may share the same JSession ID, meaning that they pertain to the same user session transaction. So what we can do is pipe to the transaction command, pass it that JSession ID field. Our results will look like this. These events look a lot larger because multiple individual events went into them, each of those events sharing the same value in that JSession ID field. So essentially here, if we have transaction events that have more than 5 individual events within them, we will see an option to expand these events and show all of the lines contained within that event. Each of these transaction events containing a date timestamp and looking like the usual events that we're familiar with. If we take a look at the fields that apply to each transaction event, we can see that quite a few of these fields have multiple values, making them multi-valued fields. Because these transaction events are going to contain multiple unique individual events that share the same value in one field, these merged fields can be treated like multi-valued fields because they have multiple values from these individual events. So if we go ahead and take a look at an example here, run a search across index equal to web, source type of access combined, across the last 24 hours. And we take a look at our field sidebar, and we'll notice that we have this JSession ID field, which is the cookie assigned at session time for each user session. I will make that a selected field so that it appears along the bottom row of each event. and I can compare the values of this JSession ID field within each event. Looking at this first event, we can see this value of JSession ID, comparing it to the value in this next event. It looks like they are the same, meaning that these two events pertain to the same user session. We have some additional events that have that same JSession ID. There may be additional events on subsequent pages with that same JSession ID, so we would like to group together all of the events that share the same value in that field. We'll go ahead and pipe to the transaction command, specify JSession ID, run that search, and we can see that we went from about 10,000 events to 911 events. And if we take a look at these events themselves, they look a lot larger. And notice I have the option to show all 15 lines. If we look closely, here's one date timestamp, here's another. That is what separates one event from another. So we can see we have multiple individual events that went into this one transaction event. If I expand it, take a look at the fields, we can see we have the status field with different HTTP status codes. We have the action field with multiple customer actions. We have the bytes field with multiple bytes, category ID, and a few others. All other shared fields of a transaction will be merged. Now, in addition to these fields, the transaction also populates a couple fields in the sidebar. Those fields are duration and event count. Duration will contain values which represent the time difference between the first and last event in the transaction. That will be represented in seconds, whereas the event count will be the number of unique events that went into a transaction. If we take a look at the sidebar, we'll notice here that we have the duration and event count fields. And if we make these selected fields as well, what we'll be able to see right below here is the number of events that are in this transaction, which are 15 unique events. The duration here is 104 seconds, which is the time difference between the first and last event timestamps within this transaction. And so we can see that those numeric values differentiate for each transaction event. Now, one thing to keep in mind about transactions is the transaction command requires the events to be organized in reverse chronological order for it to work properly. When a search directly precedes the transaction command, the results are returned in reverse chronological order. However, it is possible to configure the results to be resorted in a different order. In that case, being sure that the events are being returned in reverse chronological order, we can use the sort command on_time, sorting _time in descending order to be sure that these events are organized properly for the transaction command. The transaction command has a couple options built into it, two of those being max span and max pause. These two options allow us to control the overall time of the transaction, max span allowing us to keep track of the maximum total time between the earliest and latest events in the transaction, controlling that time range. Whereas max pause allows us to set the maximum total time between events within the transaction. Both default to -1, meaning there is no maximum time limit. And if we take a look at an example here, Let's take a look at the actions taken by customers on our website during the last 4 hours. In the field sidebar, we see the action field containing values such as add to cart, change quantity, and purchase. We want to understand all the actions users have taken in one session on our website, so we pipe to the transaction command and supply the client IP field. We will use the max span argument to filter our results to transactions spanning a maximum of 3 minutes. We can also use the max pause argument to limit our results to filter out any individual events with more than a minute between them. Our results are returned grouping together all events from the same IP address with a maximum total time of 3 minutes and a maximum of 1 minute between events. Notice in the field sidebar that we now have 2 additional fields, duration and event count. By default, the duration field is represented in seconds. To display this in a more readable format, we will pipe to the eval command and use the toString function with the duration option. We will sort our results in descending order by duration and can now display client IP, actions, and duration on a table. Now we see what actions were performed, associated with each client IP, and the overall duration of the transaction. Now we can also control what our transactions start with and end with. So let's say that we are interested in where a customer added something to their cart, and when they purchased something, we don't care what happened before or after that, just what happened in between those actions. I'm going to change up my search a little bit here. This time, instead of forming a transaction across the client IP field, we are going to go back into a transaction across the JSession ID field. And I'm going to filter on transactions that start with an action equal to add to cart and end with an action equal to purchase. Now, if we run this search, that is going to filter to 330 events. And if we take a look, we can see this first event in this transaction has an action equal to add to cart. This last event has an action equal to purchase. So we're looking at everything that happened in between when the customer added something to the cart and when they purchased that item. Now, one other example that we can go with is that the security operations team is maybe trying to track an issue in the web servers in the online store. In this case, over the last 24 hours, we want to find the 503 errors generated by user sessions in the online store and display 4 related events before it. So if we jump back over into transaction JSession ID, we're interested in looking at where we have transactions that end with a status of 503. And we'd like to see the 4 related events before it. In addition to starts with and ends with, we have a max events option built into the transaction command that allows us to filter on transactions with a maximum event number of 5. All right, so here we're now looking at transactions that end with an HTTP status code of 503. And if we wanted to highlight exactly where that 503 status code appears, we have a highlight command that will highlight whatever we tell it to. In this case, we're having it highlight the number 503 within each event. And we have a maximum number of 4 events displayed before it. So we can go ahead and take a look at events that occur before. We can also filter on transactions that start with instead of end with a value. So in this case here, we may want to find a status code of 200 instead of 503. And the 3 related events after it. So we'll specify a max event number of 4. This will filter on about 9,000 events, and we're going to look at transaction events that begin with a status code of 200, and then displaying the 3 related events after that. Now, the transaction events are just like any other event in Splunk. We can follow the transaction command by multiple additional commands. In this example here, we're using the search command to then display transactions that included a 404 error during the last hour. We can filter on just those transaction events that contain an HTTP status code of 404, and then highlight where exactly the 404 is located within these transaction events and where the JSession ID values are. In addition to that, we can pipe to transforming commands after the transaction command, where we may be interested in creating a chart to show the number of purchase transactions based on their overall duration. So if we go ahead and take a look here at filtering on successful purchases in the online store and forming a transaction across the client IP field, I may want to set the maximum time span here for these transactions to be 10 minutes. Now notice the transaction command keeps me in the events tab. I can then pipe to a transforming command such as the chart command and count by the duration field. This will display the number of transactions based on their duration. And the chart command has a span option built into it. So if I wanted to view this in, let's say, a column chart, this is what my column chart would currently look like. I can update this and add a span value of log 2. This will bucket the duration into bins using logarithm with a base of 2. That's essentially going to be the log of a given number, which will represent the exponent to which the base, in this case 2, must be raised in order to produce some number. In this case, the result of using span log 2 is setting the duration of each bin. Each bin represents an exponentially longer duration. Now, the transaction command can contain the eval function embedded within the starts with and ends with options. We may be interested in determining the length of time spent to complete a purchase by customers in the online store over the last 24 hours. In this case here, we would like to filter and evaluate where an action was added to the cart and a status equal to 200. In that case, we're going to wrap this within an eval function. Once that returns to true, we will filter on only those particular transaction events that start with and end with this particular filter. While the transaction command is often used to see what happened between point A and point B, there are times when we need to get information about transactions that did not complete. A transaction is considered closed when it meets all of the conditions specified within the transaction command. The conditions of a transaction are the options starts with, ends with, max events, max pause, and max span. The transaction command auto-populates a field in the sidebar called closed_TXN or closed_transaction. And this closed transaction field has a value of 1 or 0, depending on whether the transaction events are considered complete or incomplete. In addition to the closed transaction field, we have a keep evicted option that is built into the transaction command. Keep evicted takes a value of true or false and is set to false by default, evicting all incomplete transactions. However, as mentioned earlier, there are times when we need to get information about transactions that did not complete, which is a reason for setting keep evicted to true. Let's take a look at an example. Let's say the business operations team needs to identify the success rate of transactions on its production web servers. We're going to take a look at our web data over the last 24 hours, and we want to evaluate the transactions and provide the total attempted, total completed, and percent completed of overall transactions. What we're going to do is pipe to the transaction command, pass in the JSession ID field, group together all of the events that share the same value in the JSession ID field, and filter on those transactions that start with an action equal to add to cart and end with an action equal to purchase. And let's go ahead and run this search. Now, what we'll notice in the sidebar is we have a closed transaction field that has a value of 1, meaning that all of these transaction events are successfully completed transactions. However, if I go up into this transaction command and add keep evicted, setting it to a value of 1, meaning let's keep all of the transactions that were incomplete and evicted. That's going to bring up the event count, and it is also going to add a value of 0 to that closed transaction field. So we're looking at transactions that both satisfied and did not satisfy the requirements of the conditions. From there, we're going to run a search and only filter on those transactions that contain at least one event with an add to cart. That will bring our event count down to about 2,000. And from here, using the stats command, we are going to count and evaluate the number of events that have a closed transaction value of 0. Those will be the total failed transactions. We will count and evaluate the number of events that have a closed transaction value of 1. These are the total completed transactions. And then the overall count will be the total attempted transactions. That stats command will take us over into the statistics tab, and we will see these 3 fields and their values being created. From here, we'd like to create a new field with the eval command called percent completed that will store a percentage that will be the result of total attempted subtracted from total failed. And this is all going to be divided by total attempted. If we run this search, that's going to result in a decimal value. Since we're looking at a percentage, we want to round to the nearest integer level. And let's go ahead and add a second argument of 0 and make sure that we have the appropriate set of parentheses here. And we want to multiply total attempted subtracted by total failed by 100. All right, that's going to result in the percentage value, and we will then concatenate a percent symbol to the very end, looking at 93% of the events are completed transaction events. From here, we can go ahead and pipe on over into the table command and reformat our table here to display total attempted, followed by total completed, followed by percent completed. Since transactions are resource intensive, there are some considerations to keep in mind when creating them. One thing to keep in mind is making sure that the search that precedes the transaction command is optimized as much as possible. Including search best practices and being specific using field value pairs that will be used in the transaction command will return the events that we want to work with. We can see in this example here that the search on the left returned more events in a slower amount of time than the search on the right, which filters events in the basic search that contain an action of purchase and add to cart. The transaction command is a resource-intensive command. Therefore, it is in our best interest to use the stats command whenever possible. However, there are instances where the transaction command comes in handy, and that is when events need to be seen correlated together and displayed in the raw event view for analysis. The stats command is a transforming command. Therefore, it will transform your data into a table in visualization, allowing you to perform calculations on your data. Let's look at a couple searches that produce the same results, but one search contains a transaction command and the other contains a stats command. If we take a look at an example here and specify the time range using the earliest and latest time modifiers, looking back at data a year ago up until now, remember the earliest and latest time modifiers take precedence over the time range set in the time range picker. This search is taking a while to complete because it is searching across the last year's worth of data. We are going to pipe to the transaction command and group together all of the events that share the same value in the JSession ID field. From there, we will place JSession ID, the actions, and product names onto a table so that we can see the associated actions and product names that pertain to each session. Now, this is our result, and if we take a look at the Search Job Inspector, we can see that this search scanned over 1 million events, returned about 5,000 events in 10.199 seconds. Now let's rearrange this search. Still searching across the last year's worth of data, this time using the stats command instead of the transaction command, and looking at the unique values of action, the unique values of product name, and let's display this in a table. We're splitting that by JSession ID. And if we take a look at the Search Job Inspector, this search ran in 2.757 seconds, completing a lot faster than the search using the transaction command. Another difference between stats and transaction is that transaction has a limit on how many events can be grouped together within a transaction, and that is 1,000. Once that 1,000 limit is reached, a new transaction grouping will be created. However, the stats command does not have a limit, therefore it will keep the grouping.
A subsearch is a search that passes its results to an outer search as search terms. They can be used to narrow down the set of events you are searching on, or used with commands to combine results of one search to the results of another. Subsearches are enclosed in square brackets and must start with generating commands, like the search command or tstats. Subsearches are always executed first before passing the results to the outer search.
In this example here, we can see we have our basic search, followed by a subsearch in square brackets, followed by a set of additional commands. The results of the subsearch will have an or Boolean placed between them, and we will see that search expand into anding the results of that subsearch with those field value pairs separated by or Boolean operators. Now, we loaded in that known users.csv file earlier. We're going to use that known users.csv file within an input lookup command in a subsearch to access that lookup data and pass values to the outer search. In this example, let's go ahead and jump on over into running this search and taking a look at our security index. Source type of Linux secure. We're looking for failures, and we want to see the unknown users. We know that we've loaded in the known users from that known users.csv file. And so if we wanted to filter on the unknown users, well, what happens by default with a subsearch is we are going to and the results of that subsearch here. In this case, looking for all of the security events that contain failures and users coming from this known users.csv. If we'd like to exclude those users and only return the unknown users, we'll place a not Boolean in front of that input lookup command, run this search, and what we'll do from there is display this information within a table. Using the stats command, we will look at the unique values of the IP address, name that attacker IP. We'd like to get a count of events as failures, split by user, and we'd like to see which users had more than 3 failures. From here, we'd want to make sure that we sort those failures in descending order. And so we can see that the administrator user had the most failures. These were all of the attacker IPs that that specific user used. So in this example here, we are including a not operator before our subsearch to exclude these lookup values. And if we take a look at the search job inspector, that search job inspector will display the expanded search string. Heading on into inspect job, scrolling on down into the search job properties, what we will see here is a not Boolean operator placed in front of each field value pair coming from that known users.csv, invoked by that input lookup command within the subsearch in square brackets. In this particular search, this search is going to count the number of failures by source IP. It will return a lot of results. So we'd like to go ahead and improve this search and the results of this search, making them a bit more meaningful and filtering on those particular failed logins not coming from internal IPs. So we will exclude any IP addresses that begin with 10, get a count of events by source IP, and look at where the count is greater than 10. So look at where we have more than 10 failed login attempts. But it may still be unclear in terms of which of these IP addresses ended up successfully accessing the network. So what exactly are we trying to find? An external IP address with multiple failed attempts and one or more successful attempts to access the network with a valid password. So in this case, we'd like to use a subsearch to find these specific IP addresses that have received multiple failed events and send those to the outer search to see which ones were able to access the network. So we will build out a subsearch to do this. Let's go ahead and run an outer search and inner search separately and see what events we get returned. Running a search across index equal to security, source type of Linux secure, I would like to see the IP addresses that were accepted and were able to log in successfully across the last 24 hours. Now I can place those IP addresses on a table. However, I also want to see which of those failed to log in more than 10 times and were eventually accepted into the network. So in that case, that's going to require searching across failed passwords, excluding the internal IP addresses, and getting a count of events by source IP, where the count is greater than 10. And we can see this table here displaying those IP addresses that failed to log in with a count greater than 10. Now, of these IP addresses, which ones were eventually accepted into the network? Well, that would require passing these list of IP addresses to an outer search that will filter on Linux secure events that contain that term accepted in them. So what we'll do is we'll wrap this specific search as our subsearch. The subsearch needs to begin with a command, so this will begin with a search command. And we will precede this with index equal to security, source type of Linux secure, accepted, and from there, if we run our search, we'll notice that we're not getting any events being returned. If we look up into the job inspector here and try and diagnose why that is, in the search job properties, we'll notice that we are returning a count and a source IP in that subsearch, where we're only really interested in returning an IP address to filter on those IPs that were eventually accepted into the network. So we need to be restrictive within the subsearch on what field we are returning to the outer search, and we will do that using the fields command, passing that source IP field. From there, we will see 314 events being returned, and we want to place those IP addresses onto a table. So I will first remove any duplicates, and from there, pipe on over into the table command, listing out those unique IP addresses. Now, if we'd like to run the inner subsearch separately and take a look at how Splunk will format the results of that inner search, there is a format command that allows us to do this. I can go ahead and remove the outer search, run the inner subsearch, and we'll notice that we have two fields returned in our table. If I pipe this to the format command, the way that these results will be formatted will be as field value pairs with count and source IP, with OR Boolean operators placed between them. Which is why using the fields command and only passing that source IP field to the outer search is going to format those IP addresses with OR Booleans placed between them, and those will be used as filters for the outer search.
Subsearches are useful. but they have their limits. Multiple subsearches can be used in a search, and subsearches can be nested. But be careful, each subsearch requires an additional search on your deployment, which could quickly eat up memory and CPU.
There are multiple SPL commands that use subsearches to combine results into one set. They all take advantage of the capabilities of subsearches and are also subject to their limitations. Let's start with the append command.
Append combines results by adding subsearch results to the end of the main search results as additional rows. The security team at Buttercup Games has noticed an increase in penetration attempts to the network. They want to chart the number of failed logins at a given time for known users versus unknown users of the network over the last 4 hours. We could conduct 2 searches. First, we'd search for events that include failed passwords and invalid users from the last 4 hours, and use time chart to transform the results into a table. In a separate search, we'd look for events that include failed passwords, but without invalid user, and order them into a table, again with the time chart command. We can use the visualizations created from these searches in a dashboard, but it would be difficult to compare the results. It would be more useful to present these sets of results together in one visualization. We can do this using the append command. We write the main search, pipe in append, followed by the subsearch in square brackets. Please note, append doesn't work with real-time searches because we need both sets of results in order for append to combine them. Our search returns a statistical table with columns for both known users and unknown users. We see the results of the main search. Notice the timestamp of the first result. We click forward and find where the subsearch rows have been appended. We can see that the first row from the appended set has the same timestamp as the first row of the first set. This looks a little awkward in a stats view. However, if we display the results as a visualization, we get a great-looking graph. The results are overlaid one over the other, allowing us to compare our datasets visually. If we want to see the results in a stats table, we can use the first function to make them more readable. The first function will return the first value for a field by the order it appears in the results. To see the first function in action, let's sort our time column and look at our data. We see the results of our searches one after the other by time. Since we use the time chart command in both, we have matching bins of time for the results. We pipe our search into a stats command, using the first function to get the first value from both the known users and unknown users fields. A single result of values for each field is returned. We now have the first value for each field, but no longer have values for the other bins of time. We can get these back by changing the stats command to a time chart command. Splunk has charted our results to display the first value of each field by the time bins created by the time chart command. As an interesting note, since we want the first value from all fields included in our results, we can change our search to use only one first function with a wildcard. Here, we are telling Splunk to use all fields with the first function and keep the original name of the fields by using the as clause. While the append command adds subsearch results as rows, the append calls command adds results of the subsearch to the right of the main search's results. Here's the same search we previously wrote, using append calls instead of append. The unknown user's results from the subsearch are added to our table as an additional column, making it easy to compare known versus unknown users at a given time. There's something to keep in mind about append calls. Where append added rows, it did not merge any of the values from our 2 sets of results. With append calls, the results of subsearches are added to the results of the main search as additional table field columns. Let's look at a search using the append command. we're using earliest and latest to return yesterday's purchases of Buttercup games, and using append to join the results with a subsearch that returns purchases from the last hour. In order to display them together in a table, we are using the first function of the stats command to join results by product name. Note that some games simply haven't sold in the last hour, so their results are empty. Now, let's see what happens when we run this search with the append calls command. While the column from the subsearch has been added, something looks a little off. This is a bit of a gotcha to be aware of when using append calls. If we run the subsearch in a new window, we can see the issue. Splunk can only generate statistics for the events returned from our search. Any products that have not sold will not show up in our data. So when the column from the subsearch is appended to the main search, the results do not match the product name in the main search. Append calls did exactly what we asked for. It appended columns and no more. The join command combines the results of a subsearch with the results of a main search, but with an important requirement. Both searches must share at least one field in common. Where the append and append calls commands simply added rows and columns from one search to another, join uses the common field to group results together. We have the option to choose from 3 types of joins: an inner join, an outer join, or a left join. An inner join will only return the results from the main search that have matches in the subsearch. An outer join, or left join, will return all of the events in the main search, but will only join values from the subsearch that have matching field values. By default, the join command will execute an inner join. In our data, we have multiple source types that include values related to employee system usage. In the Win Authentication security source type, we have data of employee interactions with workstations inside the building. When an employee interacts with any of our external servers, that information is also ingested into Splunk with a source type of Linux Secure. But often, there is data in one source type that is not in another that would be helpful to us when building reports. As an example, our security team has a report that displays failed access attempts on our web and mail servers by internal users. This report could be more valuable if we knew which workstations were being used when these events happen. It would allow the team to research the possibility of an infected workstation or a bad actor within the organization. To add the workstation values to our results, we change our search to pipe the terms into the join command. We create a subsearch of the Win Authentication source type where internal IPs are present. We dedupe our results to only include one event per workstation name. As I mentioned earlier, the join command requires field values to match on. We will be using the internal IP address to do so. There is one issue. The IP address is called source IP in our main search and BCG IP in our subsearch. To be able to match, we rename the IP in our subsearch to source IP. Finally, we use the fields command to only return the needed fields. In our main search, we add the workstation field name to our stats command and run. Instantly, we notice that the usernames being used to try to log into servers do not match the provisioned workstations, making this report incredibly valuable for the security team's investigation. Since we did not use a type argument with the join command, an inner join was used. To see the difference between an inner join and an outer join, let's tweak our search a bit. We change our search to dedupe the IP field and put it in a table with the workstation name. As you can see, every result has an IP and workstation name. Changing the join command to use an outer type, we get IP addresses for all the results in the main search, not just the results that matched IP values in our subsearch. The union command combines search results from 2 or more datasets into one. These include safe searches, input lookups, data models, and subsearches. Datasets are named, meaning they are stored and accessible in our deployment using a naming syntax. The exception to this are subsearches. We will see how to use this syntax, or lack of it, in our search. In our deployment, we have a data model defined that returns all successful purchases made through the web store. We want to combine the results of the data model with search results from vendor sales. The union command is a generating command, so we need to start our search with it. Follow it with the datasets to use, separated with commas. Our first dataset is a data model. We enter the type of dataset, a colon, and the name of the dataset. We want to combine it with the subsearch, so we add a comma followed by the subsearch. Since subsearches are unnamed datasets, we use the standard search inside brackets syntax. Adding a table command with source type and product name fields, we can see that we are receiving events from both source types combined. It's worth pausing to note what's happening in the background when we use the union command. Our subsearch is acting as a wrapper, directing Splunk to invoke one of two commands, depending on the subsearch query. When used with datasets that only use distributed streaming commands, union invokes the multi-search command. Multi-search is a generating command that runs multiple streaming commands at the same time. If we use the union command, and one of the datasets is not streaming, then it runs the append command on the search head. Since we saw results combined instead of appended, we know that our search used the multi-search command. To be sure, we can use the job inspector. In the search job properties, we look at the optimized search property to see what Splunk has run in the background. Sure enough, our query invoked the multi-search command. Now let's change our subsearch so that it is no longer distributable by adding a stats count function. Notice that we now see vendor sales results appended to our results. Checking the search job properties again, we see that the union command has now directed Splunk to use the append command.
Hello, welcome to Search Under the Hood. I'm Jessica with Splunk Education. In this module, you will learn how data is stored in Splunk's architecture at index time, how to craft searches that efficiently access that data, and some troubleshooting commands in case your searches aren't performing as expected. Let's start off by discussing using the Search Job Inspector. The Search Job Inspector is a helpful tool to allow us to analyze and troubleshoot the overall performance of our search and really get a good understanding of how much impact these various different knowledge objects and components of our search are having in terms of performance. The Job Inspector can also help us get a better understanding of how to write better searches and take a look at where Splunk spent the majority of its time. We'll notice that once we run a search, the job drop-down menu has an Inspect Job option. Once we click that, it will open up the Search Job Inspector and take us into a few sections where we can start performing the analysis and troubleshooting. This Job Inspector will be available for any existing search job. Any search jobs that have possibly expired will no longer have the Job Inspector as an option. But if we take a closer look at these three sections, up at the top we have a header, which will provide information about the overall runtime of our search. We have execution costs and search job properties. And we'll start off by running a search, examining the header up at the very top, which will provide us with some information about the number of results that were returned and scanned, as well as the overall runtime of the search. And then we'll jump down into the search job properties and the execution costs. Now switching on over here into a demo and taking a look at our web data, which is stored in the web index with the source type of access combined. We are interested in looking at this web server data that has come in across the last 24 hours. And if we examine these 10,245 events that are being returned for this search, we can see that we're getting customer interactions in the online store when they were visiting this website, buttercupgames.com. We have some information about what actions the customer performed, such as adding an item to the cart. What item was that with which associated ID? So we have some product information here. And this is a fairly basic search with no commands in it. If we're interested in taking a look at its overall runtime, we can open up the job inspector, selecting inspect job, and examining that this search here completed and returned 10,245 results by scanning that same number of events in 1.272 seconds. And if we take a look at the execution costs and search job properties here, we can see where Splunk possibly spent more of its time in this search on what specific components. So notice the execution costs is broken up into a table where we have a column for duration in seconds, components, invocations, input count, and output count. We have how many times each component was invoked while that particular search was run. We have the event counts for each component, input and output count, and we have the amount of time that Splunk took to process that specific component. And we can see that the command.search component here has a longer duration time than a few of the other components. And that is because this command.search component has a few components essentially embedded within it, so underneath its hierarchy. And command.search.kv, for example, is the amount of time that Splunk took extracting fields. Command.search.lookup is the amount of time that Splunk took bringing in fields coming from a lookup based on some already existing fields that we have in our data. Command.search.raw data right down here provides information about how long it took Splunk to actually examine and read the raw data files. So we have some information about each one of these components, and if one took a significant amount of time, we may want to start troubleshooting and investigating how to resolve that and speed up the completion of that portion of the search. Along with the execution costs, we also have search job properties. And these search job properties here provide some detailed information about the search job itself in terms of the overall disk usage that search consumed in bytes. We have information as well about the earliest and latest time for our search. So here's the earliest time of our search, the overall event count. We have some additional properties here that display information about the normalized and optimized search. So the optimized search is going to be a restructured syntax when that search was run, where Splunk will try and optimize it as much as possible to improve the overall search performance. And we have some additional properties being listed here, such as the overall run duration, search providers. So those are going to be the Splunk instances that were searched across to return the results for this search. and we can see all of this information gathered together within this search job inspector. Okay, so if we are ever interested in troubleshooting the performance of the search and taking a look at how to improve the performance and seeing where Splunk spent a majority of its time, this search job inspector is going to be a very helpful tool for troubleshooting. SPL commenting is another powerful tool you can use when writing complicated searches. Adding comments to SPL searches in Splunk allow the users to troubleshoot their SPL by slowly commenting out pieces of their search, along with allowing the user to provide notes to themselves and to other users that they're sharing their search with. We can see here that these comments are wrapped in 3 backtick symbols, which is the symbol above your tab key on your keyboard. The comment will be syntax highlighted in gray, whether we're looking at a light or dark theme. And there is no limit to the number of comments you can add. There are no restrictions on where they should be placed. And let's go ahead and take a look at an example of working with comments here. If we go ahead and start off by searching across our security index across the last 24, or actually let's go ahead and take a look at the last 14 days worth of data. And we are interested in, let's say, displaying a count of these failed passwords on a table, naming the column that contains these counts based on the number of failures that have occurred across the last 14 days per day. Now, we may be interested in displaying this comparison of failures week by week across the last 2 weeks. And what we can do here is follow the time chart command with a time wrap command, specify 1-week comparisons, and we may want to provide a description or comment right before this time chart command, specifying that this is a line chart with week-to-week comparison. What we'll see is that comment is going to be syntax highlighted, the text embedded within those backticks will be ignored, and we will see some useful information and description about what the SPL is doing. So as I said earlier, comments are really useful for providing some specifications and notes to the user, but along with that, they're very helpful for troubleshooting. If we take a look at our basic search here, events being returned by the security index, source type of Linux secure, we may want to get a count of events over, let's say, the vendors. So the action of each vendor. And we can do that by counting over, let's say, action vendor, running this search, and we notice that we're not getting any results. Now, we may want to comment out that one chart command, which will allow us to run this basic search without completely removing this portion of the SPL, and try and troubleshoot why we aren't getting any results when running that chart command. And what we'll notice is that we do not have a field named action vendor. However, we do have a field named vendor action. And we can see that the different vendor actions are count, session opened, and accepted. So we can uncomment this chart command and replace action vendor with vendor action. And then build out this table.
Searches that run only once, or that query a small amount of data, are probably fine as they are. However, searches that execute repeatedly, like a scheduled search, are prime candidates for optimization. The same goes for searches that query a large volume of data. Optimizing a search usually involves making the most of tools available to us to limit the amount of data that needs to be read from disk. Generally, our goal in Splunk is to work with the smallest set of event data possible. One way to reach that goal is to understand how Splunk stores and uses event data.
Let's take a broad look at how searches are run.
They are initiated from a search head and sent out to an indexer or group of indexers, also known as search peers. These peers execute our search, then return the results to the search head where they are processed. Splunk deployments can often include multiple indexes, created by Splunk users with an administrator role. Each index represents a logical grouping of data. For example, Buttercup Games Sales Index contains all of its retail and online sales data, while its Game Index handles data from its online game servers. Index data is held in a group of data buckets.
When events are indexed into Splunk, they are placed into data buckets. Hot buckets store data as it arrives, are then rolled into read-only warm, then cold buckets, and eventually become frozen buckets for deletion or archiving. Now, let's go inside those buckets to see what happens to our data as it is ingested.
Each bucket contains a compressed journal and time series index files. The journal is where Splunk stores our raw event data. It's composed of many smaller compressed slices, each about 128 KB in size. The time series index files, or TSIDX files, are index keys to our journal file. They tell Splunk which slices of data to open up in order to find events we're looking for in a search. Here's how TSIDX files are made. Splunk takes raw events and finds each of the unique terms that exist in your data. It tokenizes those terms and writes them out to a lexicon that exists inside each TSIDX file. Each lexicon has a unique posting list array. That array gives Splunk the location of the events we're looking for inside the journal. So our bucket stores its raw data in a gzip file and creates TSIDX files as a reference to that raw data. When Splunk executes a search, it uses the TSIDX files to know where it should retrieve data from a bucket. When buckets roll over from hot to warm, Splunk creates a bloom filter based on TSIDX files. A bloom filter is a data structure used to quickly eliminate data that doesn't match our search. We don't want Splunk to read data from disk if it doesn't match our query, including TSIDX files. A bucket's bloom filter lets Splunk rule out buckets that don't have what we're looking for. To build a bucket's bloom filter, each term from a TSIDX file's lexicon is run through a set of hashing algorithms. The resulting hash sets bits in the bloom filter to 0 or 1. When a search is run, it generates its own bloom filter based on the search terms. The algorithm computed from the search is compared against a bucket's filters, which is faster than reading all of the TSIDX files. This way, Splunk can avoid entire files that it doesn't need to read.
Now let's take a look at how Splunk uses TSIDX files and bloom filters to return events from our journal files.
This search returns an hourly average of password failures over the last 24 hours. Let's look at what Splunk does in the background to get results. Splunk extracts the terms failed and root from our search and hashes them to create a search bloom filter. It identifies buckets in the security index that contain data for the last 24 hours. Then, Splunk compares the search time bloom filter to the bloom filters for buckets that have them. It rules out TSIDX files that don't have what we're looking for. Splunk checks the remaining TSIDX files for the extracted search terms. It then uses the entry in the posting list to obtain a seek address. It uses that seek address to get raw event data from the journal file. Once the raw events are loaded, search time fields are extracted. Splunk then filters the events that contain our search terms. Events that match the filtering criteria are kept, and the rest are removed. The remaining events are our search results.
In a previous segment, we looked at the Search Job Inspector to analyze our search.
Checking it for this search job, we can better understand where some of the information comes from. In the execution cost dropdown, command.search.index gives us a time to get location information from TSIDX files. Command.search.rawData tells us the time it took to extract event data from our data bucket's gzip journal files. command.search.kv tells us how long it took to perform search time field extractions, like extracting the user field. And command.search.filter shows us how long it took to filter out non-matching events. Once Splunk retrieves events from a search, we can apply SPL commands that perform statistical analysis, filtering, and formatting. We're going to look at two kinds of commands, transforming and streaming. Transforming commands operate on the entire result set of data. Because they have to wait for the results to arrive, they are executed on the search head. Once complete, transforming commands change event data into results, ordered in a table. Examples of transforming commands include the stats, time chart, top, and rare commands. Streaming commands come in two types, centralized and distributable streaming commands. Centralized streaming commands, like transforming commands, execute on the search head. They apply transformations to each event returned by a search, and the results depend on the order that the events come in. You may sometimes see them described as stateful streaming commands. Some examples of centralized streaming commands include transaction and stream stats. Distributable streaming commands can execute without waiting for the entire result set of event data. The order of incoming events doesn't matter to them. For example, an eval command operates on each event individually, so it doesn't matter whether that event came first or last. Because of this, distributable streaming commands can be executed or distributed on multiple indexers. This improves their processing time. However, if it's preceded by any commands that run on the search head, a distributable streaming command must run there as well. Some examples of distributable streaming commands include rename, eval, fields, and regex. We've just discussed a few command types, but there are many more. I've included a link to documentation on types of search commands in the notes. Now that we have a more detailed view of what's happening in a search, let's look at it step by step. The search head parses a search into distributed and centralized parts. Distributed parts of the search are sent to the indexers. Splunk uses Bloom filters, TSIDX files, and search terms to find the events we want. Distributable commands are executed on the indexer. Those results are sent back to the search head. The search head applies centralized streaming and transforming commands, and then displays the results. Now that we've broken down commands into types, let's look at 4 examples of searches and see how they work. Our first search uses time chart and stats. Note that these are both transforming commands. Therefore, the events are returned to the search head, and the search head executes the commands. In our second example, the base search retrieves events from the index. The eval command is a distributable streaming command. There are no preceding commands, therefore, eval is executed on the indexer. Results from the indexer are sent to the search head, where the time chart command transforms them into stats data. This search begins with a stats command. The stats command is a non-streaming transforming command, so the events are sent to the search head. The rename command is a distributed streaming command. However, because it's preceded by a transforming command, it's also executed on the search head. For better performance, we should move rename earlier in the pipeline, before stats, so it can happen in a distributed manner. Now, we've rearranged the search string so that the distributable streaming command, rename, precedes the transforming command, stats. We can now run the rename command on the indexer, then pass the events to the search head for the stats command to transform them. Earlier, we mentioned that Splunk tokenizes terms and events and stores them in TSIDX files at index time. It also tokenizes search terms at search time. This process is known as segmentation. During search, it compares the search tokens to event tokens, looking for a match between the two. When it finds one, it reads the matching events from disk. Segmentation happens in 2 stages, splitting events up by finding characters that we call major breakers and minor breakers. Major breakers are used to isolate words, phrases, terms, and numerical data during the first part of segmentation. Some major breakers include spaces, new lines, carriage returns, tabs, brackets, exclamation points, and commas. The second pass of segmentation then finds minor breakers within the results of the first pass to break them up further. Some minor breakers include forward slashes, colons, periods, hyphens, and dollar signs. The point of segmentation is to quickly return a set of tokens. At index time, these tokens become part of TSIDX files' lexicons and are used to build Bloom filters when buckets roll from hot to warm. At search time, Splunk uses the tokens to build a search time Bloom filter and match these terms in TSIDX files. For more information on segmentation, we have included a link in the notes. Knowing how segmentation affects search performance can help us understand what makes some searches faster than others. Let's look at how a search is broken up into tokens. We'll start with the search for an IP address. Then we open up the Search Job Inspector and click on the link to the search log. There's a lot of information in the search log. If we know what to look for, we can find the expressions that will be used to build a Bloom filter and check against TSIDX files. These are called Lispy expressions. We look through the search log to find the phrase base Lispy. This takes us to the actual Lispy expression Splunk has created from our search query. We can see the parts of our original search. Using major and minor breakers, Splunk has tokenized, separated, and reordered our search string as a Lispy expression. Splunk uses the Lispy expression to build Bloom filters and locate terms in TSIDX files. The way we craft our search affects how the Lispy expression is written and how Splunk finds and returns events. Lispy expressions use a variant of prefix notation, a mathematical notation used to write equations. In prefix notation, the operators, like and, or, and not, appear before the operands, or search terms. Here are a few things about Lispy expressions to keep in mind when crafting a search. Searching for an IP address, like we did previously, Splunk breaks search terms into separate number tokens, which can adversely affect performance. We would end up returning all events that include these numbers, not just the IP address. Phrases can also be an issue if they include breakers. In this search, our phrase includes a space, which is a major breaker. So a search for failed password returns the tokens failed and password, and would return events that contain either term. If we are looking for tokens that contain minor breakers, we can use the term directive to specify a search term as a complete value. It bypasses minor breakers for anything within the term argument. Since IP addresses use periods, they stay intact if we use the term directive. Please note, the term we're looking for must be bound by major breakers in its raw data. The image in this URL address is bound by minor breakers, so the term directive would not return it. Also, the term argument must not include any major breakers. As an example, this entire phrase is not indexed as a token, so using the term directive will be of no advantage. If there are key value pairs in your index data, you can use the term directive to match them before field extraction. You can also use the term directive when searching for field values. But there's a catch. Term will not work with aliased fields. As an example, in this search, the term directive does nothing. Splunk creates the Lispy expression for the IP as separate numbers. This is because the source IP field is an aliased field. Changing our search to use the non-normalized field with the directive, we can see that the entire IP address becomes a token. As you can imagine, this could be an issue if all your data is normalized to adhere to the Splunk SIM, causing Splunk to read more events than needed to complete searches. A way around this is to use the term directive with the IP to return the IP as a token, while keeping the normalized field value in our base search, allowing us to use the normalized field in our search while still limiting the events read from disk. Using not to exclude terms can work in Lispy expressions. This search for not password would return tokens successfully. but negating terms that include minor breakers is not helpful. If we use not to exclude an IP address, we can see one example. Splunk does not create any tokens for the IP. We end up with only index web. That means we've just told Splunk to search through an entire index, instead of specifying an IP address. This would be a good place to include the term directive. Lispy also handles wildcards in a very particular way. A wildcard in the middle or end of a string can be acceptable, but a wildcard at the beginning of a search term will not create tokens. If a search term begins with a wildcard, a token will not be created and all events will be read from disk. If the terms we are searching for include no major or minor breakers, wildcards in the middle of the string can be okay, like this. But including wildcards in a search string that contains major or minor breakers might cause inconsistent results. We know that our web server data contains the field values show.do, search.do, and success.do in the file field. We enter a search of the web index, looking for a file that starts with S and ends with do. We'd expect to get back all three of these file values. But going to the sidebar and looking at the file field, that is not what is happening. This is because we are using the wildcard to include values containing a breaker. Changing our search so that the breaker would not be caught by the wildcard returns the expected values. That said, any wildcard in the middle of a string can be costly and inconsistent. Avoid them at any cost. Whenever possible, we should restrict our search to use unique values in specific terms. Small integers and common terms like true, false, yes or no can cause many events to be read from disk. You may have noticed that searching over fields that are extracted at index time, like index or source type, show up as key value tokens in our Lispy expressions. This is because these tokens are also stored in TSIDX files. Using these fields in searches is important because they allow us to rule out large amounts of data quickly. Administrators on a Splunk deployment can choose to create other index time field extractions. This is typically done when certain search time field extractions are impacting search performance. While index time field extractions are very performant, they will increase the size of TSIDX files and will be extracted for all source types. So they should only be created when absolutely necessary. When searching for field values extracted at search time, only the value will be tokenized in the Lispy expression, and only if the equal operator is used. Other comparison operators, like greater than, less than, or not equal to, will cause field values to not be tokenized. This is because while the equal operator tells Splunk the exact term we are looking for, the others do not. Splunk can also interpret searches that rely on lookups into Lispy expressions. This search is using an automatic lookup to find price and product name values based off the product ID field in our events. We are searching for products that have a price of $9.99 and putting the product names into a table. When the search was run, Splunk knew that the price field was coming from a lookup and found the matching lookup field values in our events. In this case, values from the product ID field. It then used these values to create the Lispy expression. Looking at the expression, we can see that Splunk tokenized the two product IDs and price. Since they contain minor breakers, all three have been broken into smaller tokens. If values in the lookup field were to contain major breakers like a space or brackets, they would not be included in the Lispy expression.
Now, let's take a look at some commands and functions that can be used to troubleshoot your searches. The make results command is used to generate temporary events in memory using the _time field. If you have some static data that needs to be added at search time and is not in your index, you can use the make results command. Make results allows you to create an event containing whatever you'd like, a string, a numeric field, a random number using the random function. We can use it to create some fake data and get some practice using specific commands, such as in this example, the rex command, where we are extracting from this field created by this eval command called raw using a regular expression. Make results is a generating command. It needs to be the very first command in your search, and it is preceded by a pipe. We can then follow make results with a command such as the eval command to start creating and adding fields to the event. Let's switch on over to a demo and take a look at piping directly to the make results command. And what we see as a result is we are taken into the statistics tab. We can see _time field here with a timestamp, which is the timestamp generated from the point in time that we ran this search that contains this make results command. From there, we can start adding to this event, possibly using the eval command, creating a new field. We can name this field raw, where we are adding some possibly fake raw data here. And we are going to follow this with some commands that may allow us to extract information from it. So in this case, we may be interested in looking at extracting this value within brackets into a field. If I run this search, it will add the value of raw, which is an entire string, displayed underneath that raw column. So we currently have this raw field added to this table here, where we have a column for _time in raw, and we will then follow this with the rex command to extract some information from that field of raw using a regular expression that we specify. So what I can go ahead and do is wrap this regular expression in double quotes, run this search. We're going to extract this into a field named foo, and we can see that that value wrapped within brackets has now been extracted. So make results is very helpful in terms of possibly creating some fake data, practicing a couple of commands, such as the rex command or others, on this fake data, and then generating a set of results. The field summary command calculates a variety of summary statistics for all or a subset of fields and displays summary information as a results table. Now, the field summary command is followed by a couple of options built into it, which we see here in square brackets. It is preceded by a search, and field summary is performing common statistical calculations on all of the fields that it's working with and those fields' values, unless otherwise specified by providing a field list at the very end of the command. It is another option instead of using the stats command and the functions of the stats command to compute statistics. The benefit with field summary is you don't have to specify each stats function. It will calculate all of the common statistics for you automatically. And as I said, it must be preceded by a search, and then we pipe the results of that search to the field summary command, and we can pipe to field summary alone or pass one or more fields in the field list along with this optional argument of max vals, which is set to a numeric value, which will limit how many values of that field you'd like returned. The default of max vals is 100, where it will default to a maximum of displaying the 100 unique values of each field. And if we take a look at the output fields that the field summary command returns, These are the names of the columns in the table that the field summary command generates. We will examine each one of these in detail here. I'm going to switch on over into a demo, and let's go ahead and take a look at running a brand new search using field summary. We'll start off by looking at our web data. So we'll specify index equal to web, searching across the last 24 hours. And if we take a look at our set of results here, we have all of these fields in the sidebar. Now we may want to compute some summary statistics for these fields. The field summary command will allow us to display those statistics in a table automatically for all of the fields returned by the preceding search. All of those fields that we saw in the sidebar are going to be displayed underneath this field column. We can see a list of all of the fields being returned. And then we can see we have some additional columns in this table here, such as count, distinct count, is exact, max, mean, min, numeric count, standard deviation, and values. Starting off by looking at the count column will be the equivalent of running a stats count with that field passed in as an argument to the count function. It will tell us the number of events that contain that field, and distinct count will display unique counts of that field. It will not count duplicates. Now, if we set max vals equal to some value, such as let's say 5, for a few of these fields, is exact will return 0 because the values for distinct count are not exact. So essentially here, we're going to see is exact have a value of 0 or 1, depending on whether we are looking at the exact count of these fields. But if we're strictly limiting it to just displaying at the maximum 5 values of that field, and that field has more than 5 values, we won't see is exact with a value of 1. It will have a value of 0. So is exact is going to be set to a value of 1 or 0. It is a Boolean type field. Now, if our field contains numeric values, we will see the maximum numeric value of that field and minimum underneath that max and min column. And mean will provide us the overall average of those numeric values. Numeric count will tell us how many numeric values that field has. Standard deviation will be the amount the values of the field vary from the mean. And lastly, we will see a list of unique values for that field being listed underneath this values column. So we can see the values of the field, the overall count for each value displayed there. In this case, those values are for the category ID field. Now, if we take a look at one more example using the field summary command, and in this example, looking at some security data that came in across the last 24 hours, we can use the field summary command to just display the summary statistics for a handful of fields that we're interested in, as opposed to all of the fields that we have returned for this search. So in this example here, if I'm interested in, let's say, the source IP field. So I have the source IP field that returns IP addresses as values. And I may also be interested in the user field. I can pipe to the field summary command and follow it with this field list of source IP and user, and those will be the only two fields displayed in this table. So this example here is looking across the security index. We are filtering to just the Buttercup Games IP and source IP field and looking at a maximum of 10 values for those two fields. That's the same that we saw here with these fields of source IP and user. We can see is exact here is set to 0 for both the user and source IP fields. Now, field summary can also be used after a stats command where it is only going to work with the fields returned by that stats command in that table. So in this case, it will work with both sales and status, and then displaying a summary of the values for that sales and status field. If you need to get information about a value in your data, you can use an informational function. All of these work the same way except for the type of function. When you pass them a value, they will return a Boolean value of true or false. The type of function returns a string representation stating the type of the value supplied. Let's take a look at both the isNull function and the type of function here. Starting off with the isNull function, we can see that this function returns true or false depending on whether the value is null or not for the field passed in as an argument. So we're interested in whether we have a product ID within an event. And if there is no product ID value within an event, isNull will return true. In this if function, if the first argument being a Boolean expression returns true, we will take the second argument of yes. Otherwise, we'll take the third argument of no. We can see in this table here, there is no product ID in this event. Is product ID null? We'll take a value of yes, working off of this if function. The type of function will return the data type of the field that is passed in as an argument. So possible results will be number, string, or Boolean. And if we take a look at an example here and run a new search, let's take a look at our online transactions. And we are going to create a new field using the eval command called type of data, where this will be set to an if function. And the if function takes in 3 arguments, first argument being a Boolean expression, where if this first argument returns to true, we're using the isNull function. We're looking to see whether the action field exists within each event. And if it does not, type of data field will take the value of null. So in this case, if this returns to true, we will take the value of null because that means that action will have a null value in that event, which will make that isNull function true. If it returns false, we are going to take and display the data type of that action field. And before we run this search, if we take a look at making this action field a selected field, it is going to appear along the bottom row of each event. In this first event, we can see we have an action field with a value of view. It also exists within the second event. In the third event, there is no action field that appears along the bottom row, which means that there is no action field that exists within this event. So it will take a value of null for that type of data field. So once we run this search, we can take a look at that type of data field being displayed in the sidebar with 2 values of string and null. If we make it a selected field, we can see that there's no action field in this first event, so type of data will have a value of null. Here, type of data will have a value of string because purchase is going to be a string type. So if we're interested in displaying both action and type of data fields on a table, this is what our end result would look like. Hello, welcome to Multi-Value Fields. I'm Jessica with Splunk Education. In this module, you will learn about self-describing data and how to work with that data in Splunk, including commands and functions to help you convert and manipulate multi-value fields. Some fields in your data may contain multiple values, such as email logs that contain to, CC, and BCC values, AWS configuration records, and JSON and XML arrays. These are called multi-value fields. A multi-value field is one where within an event, we may have several values to that one field. If you've ever worked with data that had multiple values to a specific field, the way that we manipulate that data is slightly different depending on which function or command we apply. We can introduce these various different multi-value field functions that allow us to modify, evaluate, sort, and split these multi-value fields. These commands or functions typically begin with an MV prefix, with the exception of a couple functions and commands that we see listed here, such as split, list values functions, and the transaction and multi-KV commands. A great example of this type of data is JSON and XML. These two data sources are what we call self-describing data, where the structured data that we're working with is easily understood and made up of elements, attributes, and additional metadata information. Splunk is trained on structured data and will automatically detect and interpret JSON and XML formatted data and extract fields from the values within the arrays and within the collections of the name value pairs. As we're looking here at some JSON data, we have a menu with a set of objects embedded within it and a menu array that contains a few values, such as new, open, and close. And we will see that we have a very similar menu embedded within this XML syntax. So these are two examples of some self-describing data sources. Now we'll start with JSON data. We have some AWS instance system data that was ingested from a JSON formatted log file. A JSON array can contain multiple values for a single field, and curly braces specify an object grouping field value pairs, and within those objects, we may have a set of arrays designated with square brackets. These arrays are what may contain our multi-value fields. Let's go ahead and take a look at our AWS systems data, specifically looking within the systems index, source type of system info, and examine our multi-value fields. Switching on over into running a search across index equal to system, source type equal to system info across the last 24 hours. What we will see here is some JSON formatted events. And if we take a look at the field sidebar, we have a few fields beginning with CPU underscore cores that have been extracted from these JSON formatted events. Now, if I go in and select, let's say the CPU underscore cores.core field, and make it a selected field so that it appears in the selected field section and along the bottom row of each event, what we will see is this CPU cores.core field has multiple values within this one event, making it a multi-value field. So we can see that the naming convention for these fields, once they're extracted, is going to be dependent on their location path within the JSON. Now, along with that, we may have some additional fields such as root users. So if I make root users a selected field, that is also going to appear along the bottom row of each event, and we can see root users is also a multi-value field. We may be interested in working with these various different fields and passing them in to functions as arguments. If we take a look here, we can see that if we'd like to, let's say, sort the values of that multi-value root users field and pass it into this mbsort function that we'll discuss in a little bit, we'll see that we have to rename that field prior to passing it into a function as an argument. Reason for that is because this field is named with curly braces at the very end, and those curly braces may return inconsistent results. So what we recommend is renaming root_users as root users, excluding those curly braces, and then sorting the values of that multi-value field, passing in that new name as an argument to this mbsort function. So as we can see here, if we pass in root_users with its original name, including those special curly braces characters, we'll notice that Splunk is going to create an entirely new field. The eval statement here is going to essentially create a new field excluding the curly braces named root_users. We'll see that new field in the sidebar, which will contain the values of root users in all uppercase. So in this case here, it will create an entirely brand new field. Best practice is going to be to rename that field and then pass it into functions as an argument. Now moving on over into XML, Splunk has a little more difficulty assigning a pre-trained source type and automatically detecting XML formatted data. You will have to create a source type and teach it or give it the appropriate settings or properties that it needs to properly break your XML events and extract timestamps. However, when it comes to fields, Splunk does not extract them for you by default with XML-based data. You will have to go in and extract field information yourself using something like the spath command to make working with your XML data easier. The spath command extracts fields from self-describing data. It can be used with data formatted with either XML or JSON. We will take our XML formatted events and pipe them into the spath command. The fields will appear in your fields sidebar. We can see some examples of those fields here. And they are named by their location paths separated by periods. What we'll see here is the opening element followed by its sub-elements and then the name of the field and its values. So for example, root.row.status is going to follow this location path in the XML hierarchy. We can pipe to a rename command after the spath command and rename these fields. Or alternatively, we could create an alias for them if we wanted them to be persistent renames. But let's talk a little bit about the syntax for the spath command. The spath command has a few options built into it. We can see these options syntax highlighted here in green. Starting off with the input field is the field from which the data is being extracted. By default, it is set to _raw, which is extracting information from the raw events. There may be instances where we'd like to extract data from a specific field whose values are XML or JSON formatted, which would be an example of providing an alternative field name to the input argument. Now, the output will store the extracted information in this field. It defaults to the value of the path argument, which defaults to extracting all fields from the first 5,000 characters of the input option. And then lastly, we have the path option here. And this path argument will allow specific values of a location path. We can specify the location path of the values that we'd like to extract. Now, one thing to keep in mind is that Splunk will not parse out JSON unless the entire event is a JSON object. Otherwise, spath will not work. Therefore, if it's not entirely JSON, what you could do is extract the part of the event that is JSON into a field using something like the rex command, and then use spath to parse the field. But what I'm specifically referring to when I mention location steps as a value of the path argument in the spath command is the field names and their position in the XML or JSON and the values that we'd like to extract from a position in the array using an index. And when we're specifying index, that is a position within an array in terms of discussing JSON or XML formatted data. In JSON, numbering begins with 0. In XML, it begins with 1. And if the index refers to an XML attribute, you must specify the attribute name with an @ symbol. Now let's jump on over into a couple of examples here using the spath command. In this scenario, the IT team wants to create a table containing status, description, and status type from data in an XML file. Let's switch on over into running a brand new search. And this time, we would like to take a look at a source type of status definitions within the systems index. And we can see here, this is an XML formatted event that contains row elements, all embedded within an open and closing root element. And we can see that we have information about HTTP status codes, their description, and their type. We may want to place all of that information in a table. However, notice in the field sidebar, we do not have any fields named status, status description, and status type that we can use in our table command. However, we can automatically extract these fields by piping directly into the spath command. And if we pipe into the spath command alone, the input will default to _raw, therefore it will work with this single raw event. and the fields in the sidebar and their names will be based on their location paths in the XML. Therefore, we see a field here named root.row.status, root.row.status description, and root.row.status type. Now, placing these fields on a table that begin with root, instead of having to type out each of these fields, there is a shortcut where we can specify a wildcard in this table command for any fields that have the same prefix. All of these fields begin with a root followed by a dot symbol. We can specify that as the prefix followed by a wildcard. Splunk will look for all of those fields that begin with that value and place them onto a table. So if we take a look at our table, we have these 3 fields. And if we are interested in, let's say, renaming them and cleaning up our table and maybe providing a name of status, status description, and status type, we can pipe to a rename command and again, use a wildcard. In this example, we're saying that we would like to rename all of these fields that begin with root.row, followed by different set of values, and rename it using whatever values each field has right after that root.row prefix. If I run this search, we can see those field names being updated within the table. And we are now looking at a column of HTTP status codes, status description, and status type values. Now switching on over into some JSON data. We will jump back into the systems index, source type equal to menu JSON. And in this scenario, the dev team wants to display a table of pop-up menu values from data in a JSON file. Expanding this event here, we can see we have a menu that contains pop-up items. The values here on click are creating a new document, opening a document, closing a document. We can see in the field sidebar, Splunk attempted to extract fields menu.popup.menu item on click with these 3 values, menu item values, and then we can see information here in terms of menu ID and menu value in the sidebar. Now, we may be interested specifically in extracting a field named menu items that contains new open and close. And we can see here, there is already a field that was automatically extracted with those 3 values, but using the output option of the spath command, this is going to be the field name that we will extract these 3 values into. And from there, we need to provide a location path to tell Splunk how to extract those values. So specifying here the location menu.popup.menu item, which is an array. We can see these open and closing square brackets. We would like to extract the values new, open, and close. So we will specify .value, run this search. This will automatically extract a field named menu items in the sidebar, and we will be able to place menu items with those 3 values in a table. Now heading back over into one last example here, switching back over into XML formatted data. we are going to look at some information regarding books and their publication dates within the library XML source type systems index here, expand our time range to all time. Reason we're specifying a time range of all time is because we have just one single event that came in on October 15th, 2018. And we can see here we have some XML formatted data with information about each book, the year it was published, author, title, and no fields for this XML formatted data being extracted. So let's say the docs team wants to extract a table of book publication dates from this XML file. In this case, we will go ahead and pipe on over into the spath command. We will specify an output, which will be the publication dates field, and the path to the year published, which is an attribute embedded within this title element. This location path will be purchases.book.title, and embedded within the title is an attribute called year published, which will extract these years into this publication dates field. We will see that publication dates field in the sidebar, and then we can move forward into placing that field on a table and treating it and using it just like any other field. So we just walked through a set of these examples here working with XML and JSON formatted data using the spath command. Now, I mentioned earlier that the spath command only applies to JSON and XML formatted data. If we are working with some unstructured data that is not fully JSON, but has some JSON embedded within it, we can assign the input to the spath command as the field that contains that JSON formatted data, which is what we're looking at here. Within this source type of server log, we have some JSON embedded, which is stored in a system info field, and that field has already been extracted and appears in the field sidebar. We can provide that system info field as a value to the input option within the spath command, which will move forward and extract the values for total RAM, RAM percent used, CPU percent used, available RAM, inactive and free RAM, used and active RAM as fields in the sidebar. In this example, _raw is no longer being used as the default. System info is the field that is used as the input. As an alternative to the spath command, you can also use the spath function of the eval command. Spath is a command, however, it is also a function of the eval command, and the spath eval function accepts a location path as its second argument and will allow the values of that location path to be written to a newly named field. In this example, we are passing in _raw as the input source field and root.row.status description wrapped in double quotes as the location path for the values that we'd like to extract. One benefit of using the spath function of the eval command is that we can wrap the spath function in other functions that the eval command supports, such as the upper function for text formatting, where we would like to place all of the values returned by the field extracted by spath in all uppercase, as we see in this example. The multi-kv command can be used to extract field values from table formatted events. Data comes in a variety of different formats. One example is data formatted in a tabular manner, such as netstat logs, which are giving us information about network connections. If we try to use the spath command with this kind of data, we will not receive an error. However, we won't see any fields appearing in our sidebar because this is not an XML or JSON structured data format. Therefore, the multi-kv command will be applicable to these table formatted events for extracting fields. For this type of table formatted data, we will need to use the multi-kv command. We can see here, these netstat logs contain a header row, and down each column, we can see the values for each field in that header row. The multi-kv command will take the header row for each event and extract those column headers as the field names, and their values underneath will be the field's values. Multi-kv will separate each row within each tabular event into its own individual event, and we will see events with the same date and timestamp if they came from the same original event. Each row represents a record in this formatted data, which is why we are extracting each one into its own event. Let's go ahead and switch on over into a demo and take a look at some netstat logs and apply the multi-kv command. Running a search across our main index source type of netstat across the last 24 hours, what we will see here is 1,470 events being returned. Our events are organized in a table formatted manner. We can see the header row contains these field names, and down each column, we can see the values for each one of those fields. However, those fields are not extracted in the sidebar. What we can do in our search is follow this with the multi-kv command, and we go from about 1,400 events to 103,000 events. Notice in the sidebar, we have a field named foreign address, local address, proto, recvq, sendq with the values. And we can see we have multiple events with the same timestamp because they came from the same original event. Multi-kv creates an event for each row in that original table formatted event, and the field names are derived from the header row of each event. Now, the multi-kv command has a fields and filter option built into it. The fields option allows the user to restrict the multi-kv command to only extract the named fields and filter on the specified values. The arguments supplied to the filter option are treated like they are connected using an OR Boolean operator. So if we head back over into our search and we restrict to only extract, let's say, the local address, foreign address, and state fields, we can specify those fields here: local address, foreign address, and state. Those will be the three fields that are going to be extracted in the sidebar. And let's say we wanted to filter on values for those fields, specifically these state values of establish and listen here. So we are going to provide those in the filter, and we will see those appear in the sidebar as the two values of that field. So we can see here that the arguments for the filter option are treated like they are connected using OR operators. The list function can be used with stats or chart and returns all values for a given field. The list function of the stats command lists all the values of a field passed in as its argument. We can rename the listed fields using the as clause with the new name. Otherwise, the name will be the name of the function, which is list followed by its argument. We can split by one or more fields. And if we have more than one value listed, that is going to pertain to a multi-value field. The order in which they're returned is the order of the events. We can see here that we are listing out the values of s_hostname, naming that column websites visited, splitting by cs_username. We have usernames in the leftmost column. We have the websites each user visited in the second column here, named websites visited. And we can see that websites visited here is a multi-value field, meaning that that field has multiple values in this one event. And we can see that this user of a Poochie@buttercupgames.com, for example, visited ebgames.com, and we have 3 instances of that value. The values function works very similarly to the list function and can also be used with stats or chart. Now, the values function is going to return unique values of a field and display those within our table. Once again, it can be renamed using the as clause. We can split by one or more fields. And if we take a look at a comparison between the two, we'll notice that we are no longer listing out any duplicate websites visited. We are only looking at unique websites that each user has visited. And right down here, this specific user has happened to visit 2 unique different websites. These are just a couple examples of functions you can use with multi-value fields. I have added a link to additional stats and chart functions to your notes. One last command to discuss is the transaction command. The transaction command is used to group together events that share the same value in one or more fields, all pertaining to a transaction where these events are related in some way. When we're forming transaction events, multiple events are combined into one large single transaction event, which brings in fields with multiple values, creating multi-value fields. In this example, we can see we're forming a transaction across the client IP field, grouping together all of the events that share the same client IP, placing client IP status and action onto a table. And what we'll notice if we run this search in the browser within Splunk, we will go ahead and specify index equal to web, source type equal to access combined across the last 24 hours. And we may be interested in grouping together all of the events that share the same client IP address. In this case, we will form a transaction across client IP. We will see 181 transaction events being returned, and we can make action a selected field. What we'll notice is that this action field has multiple values within this single transaction event. And if we wanted to place that information onto a table, we can see the associated client IP, status code, and action. This particular client is associated with these multiple HTTP status codes and actions. Status and action both being multi-value fields created by forming these transactions. In this segment, we'll learn how to create multi-value fields using the split function and the make_mv command. The multi-value eval functions that we'll be discussing in this segment will all be functions of the eval command and can also be used with the field format command and where commands. We can also use these multi-value functions as arguments of an eval function of the stats command. The split function can be used to create multi-value fields from a single value field using a specified delimiter. The split function allows users to create multi-value fields out of single value fields, and the values are separated based on the delimiter that we specify. We can see here the first argument is going to be a single value field, and the second argument is going to be the specific delimiter that exists within that field to split it into multiple values. One example we can see here is field A, which is a single value field passed in as the first argument, contains semicolons as the delimiter. We'd like to split each unique value based on the placement of that semicolon and store it in this new field created using the eval command, which will be a newly created multi-value field. If we take a look at an example of the split function and run a search across the web index source type of access combined, we are interested in our successful purchases in the online store. And we are looking for events that contain a product ID field. If we take a look at these events and our fields in the sidebar, we'll notice that the product ID field contains product ID values with this hyphen symbol embedded within these values. And we would like to create a new field out of this single value field that splits each of these values based on that delimiter. In order to do that, we will go ahead and pipe to the eval command, create a new field called product codes, and set that equal to the split function, which will take in the single value field as its first argument. Second argument will be the unique delimiter, and we will now be creating a new multi-value field called product codes, which will appear in the field sidebar. If I make it a selected field, I will be able to see that field and its values that exist within this one event being a multi-value field. And from here, I would like to place these onto a table. These product ID single value fields were converted into a multi-value field called product codes based on the unique delimiter. The make_mv command also creates a multi-value field from a single value field, but can use either a supplied delimiter or regex. The make_mv command is similar to the split function, but the key difference is it doesn't create a new field. It replaces the single valued field that you pass in as an argument with the new values. The delimiter is specified as a string value of the delim option. And we also have a tokenizer option, which allows for matching on a regular expression. If the tokenizer is used, the regular expression must contain a capturing field to repeat match against the text of field. Each match will be a new value in the new multi-value field. Now we have different types of commands in Splunk, and these different types of commands run on the different Splunk components, whether it's a search head or an indexer. Make_mv is a distributable streaming command, meaning it can execute and run on multiple indexers in parallel. Let's go ahead and take a look at an example using make_mv. We are going to run a brand new search and take a look at our web index. Source type of access combined. Action equal to purchase, and product ID equal to wildcard. We're going based off of the example that we just worked with the split function. However, this time we will use the make_mv command. and we are going to pipe to make MV, pass in a delimiter, which is going to be the hyphen symbol and the name of the new field that we're creating. Or actually what we're doing is we are rewriting the values of product ID based on that delimiter and splitting those values, creating a new field of product ID, which is now multi-value. So notice that we are essentially replacing the values of that field at search time. If we would like to write these updated results that are generated by the makemv command and create a separate field instead of overwriting the original field, we can create an eval with a new field name called product codes, copy the product ID field and its values to product codes, and then update product codes, keeping the original values of product ID and creating a new multi-value field of product codes using that makemv command. Now, taking a look at one more example here within the web index, we have a field here named URI_path. We're going to set it equal to a wildcard. And if we take a look at our field sidebar here, we have information about the URI path. We're looking for events that contain that field, and we would like to place that field onto a table. We are going to remove any duplicates using the dedupe command. And then create a brand new field called MV URI path. So multi-value URI path. All right, so this is going to be a copy currently of URI, the original URI path field. And we will pipe to the makemv command, this time using the tokenizer option, and setting the tokenizer option equal to a regular expression, which is going to match on one or more word characters, and it will go ahead and extract based on the regular expression, write to MVURI path these multiple values, essentially extracting these word characters from the original URI path field, creating a multi-value field called MVURI path using the makemv command with the tokenizer option built into it. Using that tokenizer option does require knowledge of regex in order for it to work. The eval command allows you to use functions to evaluate multi-value fields, including the mvCount, mvIndex, and mvFilter functions. The mvCount function counts the number of values for a specified multi-value field. mvCount will count the number of values in a multi-valued field for each result. If the field passed into the mvCount function has no values or doesn't exist, mvCount will return a value of null. The mvCount function takes in a multi-valued field as an argument, returning a numeric value as the count value. In this scenario, the sales team wants to know how many transactions in the online store over the last 24 hours contained more than 4 actions within half an hour. Taking a look at our web index, source type of access combined, we are going to form a transaction across all events that share the same JSession ID. With a maximum time span of 30 minutes. And the sales team would like to know how many transactions in the online store contained more than 4 actions, more than 4 customer actions in the online store. We can take a look and get a count of events, specifically transaction events, that have larger than a count of 4 actions using the MV count function and pipe to the eval command, creating a new field called action count, passing action in as an argument to the MV count function, running that search, seeing a field here being created, and filtering on where we're working with transaction events that are greater than 4, that will return these 22 events. The MV index function assigns an array index to a multi-value field and returns a value based on a given integer. Now let's go ahead and take a look at the MV index function's syntax before we run a search using the MV index function. We use MV index to reference and retrieve a value in the position of the array or multi-valued field that we're working with. It begins at the 0 index or at the 0 position in the array. So if we wanted, let's say, the second value of that multi-valued field, we would specify an index equal to 1. And this MV index function takes in 3 arguments, third argument being optional, first argument being a multi-valued field, and the second argument is the starting index or starting position for the value that we'd like to extract. If there is no end index provided, we will extract the values from the start index, and only the value from that start index is returned. If the end index is specified, Splunk will return values between the start index and end index integer. Now, in this next scenario, sales wants a count of all product names sold yesterday on the Buttercup Games website whose second product code's value is a value of SH. All right, and we are going to use the split function that we talked about earlier in this search along with the MV index function. Jumping back over into our basic search and adding on successful purchases in the online store, where we are looking for events that contain the product ID field. We are going to create the product codes field, which will be the result of the split function, converting the values of product ID to multiple values stored within this newly created multi-value field of product codes. In addition to that, we will create a second field here named product code 2, which will be set to the MV index function. And we would like to take the first index value, meaning the second value of each multi-value field, which in this case is the product codes field, and store that in this product code 2 field. So we will see in the field sidebar that we will have a product codes and product code 2 field being created. And we would like to filter on those products with a product codes value of SH. Using the where command, we will specify where product code 2 is equal to a value that contains SH, And let's take a look at this information in a table. We will count the number of events that contain the product code 2 field and split that by product name and display that information in a table. The MV filter function allows you to filter multi-value fields based on a Boolean expression. We can narrow results based on values in a multi-value field using MV filter. The MV filter function takes a Boolean expression as an argument, which could be a function that returns true or false. Let's go ahead and use the MV filter function to match on values of root users that begin with C and store that in the names field. In this example, we are renaming root users, passing it in as an argument to the match function, which is embedded within the MV filter function. The match function is a function of the eval command that returns to true or false, depending on whether the values of root underscore users match this regular expression. On the very right-hand side, we are also embedding a like operator, which is going to return true or false, whether the values of root user begin with a C followed by anything else, this % symbol being a wildcard. This Boolean expression returns to true or false, and MV filter will then filter on any names that begin with C. These are two separate solutions to return the same set of results. As long as it's a Boolean expression that can be plugged into the MV filter function, we will see the same set of results being returned there. We can analyze multi-value data in Splunk using eval functions and the MV expand command. The MV sort function can be used to sort values in a multi-value field lexicographically. The MV sort function takes in a multi-value field as a single argument and sorts the values of that multi-value field in lexicographical order. Taking a look at an example of a set of values, what we can see here is lexicographical order sorts the UTF-8 encoded strings, sorting numbers first based on their first digit, followed by uppercase letters and then lowercase letters. These set of values here have been sorted in lexicographical order on the very right-hand side. Numbers sorted first based on that first digit. In this example here, we want a list of users for each virtual AWS instance for the last 7 days. Let's go ahead and take a look at this data here across the last 7 days and run an entirely new search. In this example, we are searching across our system info data, updating the time range to the last 7 days. And if we take a look at our field sidebar, we have the root users field. We would first like to rename this root users field as root underscore users. And we're also going to be working with the system field. We will rename it as system. And we can see that system field has the AWS system information as its field values. Now, based on these root users, we would like to sort the root users in lexicographical order by passing that field in as an argument to the MV sort function. We will update the root users field with the eval command, pass it in as an argument to the MV sort function, and remove any duplicates for the combination of the system and root users field. And at this point, place this information onto a table. Looking at a list of root users by system across the last 7 days, we can see these users being sorted in lexicographical order. And we have a list of users for each virtual AWS instance across the last 7 days here. The mv-zip function allows you to concatenate values from two multi-value fields using a delimiter. mv-zip combines two sets of multi-valued fields, pairing their values together in a new set and combining the first value of field X with the first value of field Y, second value of field X with the second value of field Y, and so on and so forth. The default delimiter that is used is a comma if one is not specified. And one requirement is that both of these fields that are passed in as the first two arguments should have the same number of values. If we take a look at an example here, the IT team wants a report for the last 24 hours of all of its AWS systems, along with each of its cores and the percent used for each core. They would like a presentation of the core along with the core percent used in a single field, concatenated by a colon and a space, and to show only cores with usage more than 0. All right, so let's go ahead and maybe take a look at this search that we're currently looking at. We can see that we are going to create a new field called zip percent used, which is going to combine the values of core and core percent used. This is the unique delimiter here is a colon, and we'll be able to then search for where the zip percent used is not equal to a value that ends in 0, and then display those out in a table underneath this newly created field called CPU core usage. Now, if we take a look at a pretty simple example, one that's a little bit different than the one that we see on the slide here, let's jump back over into our web server data. And we have a field in the sidebar here called method. We have two different methods here, post and get. And we would like to display the unique methods and HTTP status codes out on a table. And along with that, we are going to combine and zip these values by creating a new field with this eval command using the mv-zip function. We'll pass in method as the first argument, status as the second argument. And that's going to result in this zip field with these set of values. The comma is being used as the default delimiter. If we would like to use a colon as the delimiter, those values are then going to be updated. One thing to keep in mind, if both of the fields don't have the same number of values, we will see incomplete results. So both of those two arguments of the mv-zip function need to have the same number of values. The mv-join function allows you to concatenate multi-value field values into a single value field, separated by a delimiter. The result of mv-join is a single value field. mv-join will take a multi-value field as the first argument. Second argument will be used as the separator. It will link together the values of the multi-value field with the specified delimiter, outputting a single value field and joining them together into one. In this example, the IT team wants to see a list of root users concatenated with a comma on each of its AWS instances during the last 60 minutes. Those users will be sorted and then will be joined with a comma using the mvJoin function, creating a single value field of all of those users. Now, the mvMap function performs an operation over the values of a multi-value field, then returns a multi-value field as a result. The mvMap function takes in a multi-value field as its first argument. Second argument is going to be an expression where it will apply an operation over the values of a multi-value field and then return a multi-value field as a result. In this example, we are looking at our system info data, and we are mapping this expression, %used divided by 2, to all of the values of %used. All of the values of %used will be divided by 2, the result being stored in this %used field, resulting in values of 0.50. The mvappend function takes 2 or more single value fields, multi-value fields, and strings and returns a multi-value field as the result. mvappend will take in 2 or more single value fields, multi-value fields along with strings, and will return a multi-value field as a result. We can see here field A, the string ABC, and a multi-value field is passed in as an argument. mvappend allows for a combination of different types of values passed in as an argument. It will append all of those values together into a newly created field. One example is appending values to an event created using the make_results command. The make_results command is a useful command for creating data to test and troubleshoot with. It will create a single timestamp, and we can start adding fields, possibly testing some fake data to that event, and possibly appending values to this newly created field called products. If we take a look at this example and pipe on over to the make_results command, we will create an event with a single timestamp, create a new field here called manufacturer, where we are adding the value of Donko, the city of Shenzhen, and creating the fields country and products. Now, before we even add products here, let's go ahead and run this search and take a look at these fields being added to this event. So we're looking at a table here with different fields and a single event for each row. And we will create this field called products that will be equal to the mvappend function, which will take in 3, in this specific example, 3 strings. Holy Blade of Gouda, Mediocre Kingdoms, and Dream Crusher. We can see those 3 values being appended, resulting in a multi-value field called products. And finally, the mvexpand command can be used to create a separate event for each value contained in a multi-value field. The mvexpand command is going to take a multi-value field and create a new event for each value of that multi-value field. In this example, we are passing in that multi-value field, expanding multiple events, and having the option to set a limit on the number of new events that are returned as a result of that mvexpand command. mvexpand is a distributable streaming command. And if we take a look at an example, let's jump back into our index of systems, source type of system info. And once again, we will rename root users and system fields and place them onto a table. Now notice that root users here is a multi-value field. Once we follow this search with the mvexpand command, Splunk is going to create new events separating each value of this multi-value field into an entirely new event. So currently we have 6,168 events being returned. We will branch out into 6,171 events being returned, expanding each value of root users into its own event. Now, as a result, using mvexpand, we are creating new events in memory. So in order to preserve memory usage and overhead, an alternative option would be to use the fields command before the mvexpand command to extract and specify only the set of fields that we are interested in working with. This will improve the overall search performance. Notice this search on the left-hand side using the fields command returns in 4.07 seconds, whereas the search on the very right-hand side that does not use the fields command returns in 6.911 seconds. The search on the left using fields being faster.
Hello, welcome to Search Optimization. I'm Chris Amade with Splunk Education. In this module, my colleague Jessica and I will help you to learn about how to optimize a search, accelerate reports and data models, and about some commands you can use to best access those data models. You may already know a little about search optimization, but let's start with an overview of the basics. Search modes determine how much field data is returned and, as a result, affect how fast the search completes. There are 3 search modes to choose from: fast, smart, and verbose. Fast mode prioritizes speed over completeness. Field discovery is disabled for this mode, only returning information on default fields and fields required to fulfill your search. Verbose mode prioritizes completeness over speed, returning all extracted fields, an event list, and an event timeline for every search. Due to the increased size of the search payload, verbose mode is the slowest search mode option. Smart mode is the default search mode, balancing speed and completeness. If a transforming search is run, it will behave like fast mode. If a non-transforming search is run, it behaves like verbose mode. Using time to limit the events returned is the most efficient way to filter events. The less data you have to search, the faster Splunk will be. After time, the default fields of index, source, host, and source type are the most powerful. These fields are extracted at index time, so they will not need to be extracted for each search. The more you tell the search engine, the more likely it is that you'll get good results. It's better to search for failed password instead of just password. Inclusion is generally better than exclusion. Searching for access denied is better than searching for not access granted. When possible, use the or in operators instead of wildcards. Apply filtering commands as early as possible in your search. Filtering early limits the number of events returned, making future manipulations of the data faster. The Splunk Search Scheduler allows you to define and manage when scheduled reports and alerts will run. There's a limit to the number of searches Splunk can run concurrently, generally based on the number of CPUs, which is tunable. When Splunk is running too many searches, the next search that Splunk chooses to run is based on a priority. When a slot becomes available for Splunk to run a search, the first choice will be ad hoc historical searches. These are searches that are run manually by users, usually through Splunk Web. After ad hoc historical searches, the next searches considered to run will be manually scheduled searches using real-time scheduling. Don't get confused by the term real-time here. We're not talking about real-time searches, which run continuously. In this case, the phrase real-time is referring to a scheduling mechanism. With real-time scheduling, searches actually have the ability to be skipped. Next, after real-time searches, Splunk will choose to run manually scheduled searches with continuous scheduling. Continuous scheduling differs from real-time scheduling in that searches aren't necessarily skipped, but they can be paused and for extensive periods of time. And then finally, the last consideration is automatically scheduled searches. These are searches that were put on the schedule by automatic processes that maintain things like acceleration summaries and auto-summarization. If you want to find out more about real-time and continuous scheduling, please refer to the Splunk documentation. While Splunk can scan massive amounts of data, the time it takes to return results will be affected by the number of events summarized in the report. In cases where you're running a one-off search, this might not matter much, but it quickly can become impractical when you are using these searches in frequently run reports and dashboards, taxing your deployment and possibly slowing down search result times for all users. Splunk allows you to create summaries of your event data. These are smaller segments of event data populated by background searches that only include the data needed to fulfill the search. When you run a search against one of these summaries, it should complete significantly faster since the data you're searching over is much smaller than the original raw events. Splunk has 3 data summary creation methods: report acceleration, summary indexing, and data model acceleration. Report acceleration will use automatically created summaries to speed up completion times for certain kinds of reports. Summary indexing enables search acceleration through the manual creation of summary indexes. These indexes exist separately from other indexes in your deployment. Data model acceleration will accelerate all fields defined in a data model. Data model acceleration is the easiest and most efficient option and will typically be your first choice. Summary indexing is recommended only for reports that don't qualify for acceleration and is out of the scope of this module. If you're interested in learning more about summary indexing, I've added a link to your notes. Now, let's head over to Jessica and learn about report acceleration.
Report acceleration is used when you want to accelerate individual reports and is easy to set up. When you create an accelerated report, Splunk will run the report and populate an acceleration summary. Acceleration summaries, at a basic level, are stored search results populated every 10 minutes to keep the data up to date. Summaries are stored as file chunks by time, alongside buckets in your indexes. When the report is run, Splunk will use the events stored in the summary to return results. As an added bonus, if the summary is created from a shared report, any search created by a user with access to the report will also use the summary when possible. Before you can accelerate a report, there are a few rules you need to follow and some items to be aware of. The search mode for the report must be set to either smart or fast. To accelerate a report, users must have the schedule search privilege. The power user role has this by default. If you delete all reports that use a summary, the summary will also be deleted. Most importantly, you need to be aware of the commands your report is using to be able to accelerate them. The 3 types of commands that are important to report acceleration are streaming, non-streaming, and transforming. Streaming commands operate on each event as the event is returned by the search. Eval, search, fields, and rename are examples of streaming commands. Non-streaming commands wait until all events are returned from the indexers before executing the command. Not only do these include commands like transaction, but many streaming commands like eval and rename become non-streaming when used after a transforming command. Transforming commands order the results into a data table. Cells in the table are populated with numerical values from the results, where they can be used for statistical purposes. Examples are the stats, chart, top, and rare commands. Accelerated reports must include a transforming command. If there are any commands before the transforming command, they must be streaming commands. If you use any commands after the transforming command, they must be non-streaming. So as an example, if we have a report based off of this search, we will not be able to accelerate it. This is because it does not include a transforming command. If we added a stats command to the search driving our report, it would be available for acceleration. We would also be able to accelerate the report if non-streaming commands were used after the transforming command. If we use a non-streaming command before the transforming command, we would not be able to accelerate the report. Let's see report acceleration in action. We enter our search, run it and click Save As and select Report. We give the report a name and save it. We can choose to accelerate the report from the Report Created dialog box, from the report itself, using the Reports menu, or from Searches, Reports, and Alerts in the Settings menu. To enable acceleration, we click the Accelerate Report checkbox and select a summary range. The summary range is the range of time for the data we want accelerated from the current time. In this example, we are selecting 1 month, which will accelerate the last 30 days of data. A search that is run within this time range would only use the summary to return results. If a search time range exceeds the summary range, Splunk will need to go to the source index to return the data that does not fall within the summary time range. Clicking Save, Splunk will start building our acceleration summary. Returning to our reports list and clicking on the report, results are returned. Looking at the job inspector, we can see that the summary was used for the search. Moving to the Search and Reporting app, if we run a search that can use the summary, Splunk will use it to return results. If we try to accelerate a report that does not meet the requirements we mentioned earlier, we receive a "This report cannot be accelerated" error. Even when Splunk allows you to accelerate a report, there can be times when an acceleration summary is not created and searches will not be accelerated. This can happen when there are too many events in the summary range. If Splunk estimates that a completed summary will exceed 10% of your total bucket size in your deployment, it will suspend summary creation for 24 hours. Splunk will check periodically and create the summary if the report meets requirements. Splunk provides a Report Acceleration Summaries page that gives you details on your summaries. We see reports that are using the summary, summarization load, number of times the summary has been accessed, and the current status for the summary. The summarization load is a calculation of the effort to update the summary. The current status displays the percentage of the summary that has been completed or a status value. Clicking on a summary ID, we get more details on the summary and some action buttons to verify, update, rebuild, or delete the summary. Under the Details heading, we see things like how much disk space is being used, the summary range, number of buckets included, and the number of data chunks the summary is stored in. If you ever find that an accelerated report is not returning the results expected, make sure that any of the knowledge objects related to your search have not changed. If they have, you will need to fix the search that drives the report and rebuild the summary. Data model acceleration works a little like report acceleration in that files are created and accessed to return search results. In data model acceleration, this is called a high-performance analytics store. We will discuss how these files are used to speed up searches later in this module. There are two types of data model acceleration, ad hoc and persistent. Ad hoc acceleration takes place automatically whenever a user runs a pivot on a data model that has not been persistently accelerated. The files that are created for the acceleration are stored on a search head and only exist while the user is actively using the pivot tool. By default, when you first access the pivot tool, it will automatically run over all time, which means your initial acceleration will include all of the data in your index defined by your data model constraints. With this much data being accessed, the initial pivot will complete slowly as the acceleration summary is built. After the initial build, the pivot editor will use the summary for further actions taken in the editor, and will rebuild the summary to match the time filter selected, causing pivot performance to improve as the pivot editor is being accessed. While the pivot editor will use the summary data, reports created in the pivot editor will not. As you can imagine, having multiple users running ad hoc acceleration could tax your deployment. To address this issue, Splunk allows us to define persistent data model acceleration. The files created for a persistent acceleration are stored alongside buckets on the indexers and exist as long as the data model exists. They can be scoped to particular time ranges and are maintained on an ongoing basis. Summaries for persistently accelerated data can be used by all users, where ad hoc summaries only apply to one user. There are some restrictions when creating a persistent data model acceleration. A user with the Accelerate Data Model privilege or an admin role is required. Private data models cannot be accelerated. Once a data model has been accelerated, it cannot be edited. While all data model datasets can benefit from ad hoc acceleration, only event dataset hierarchies and search dataset hierarchies based on root search datasets that only include streaming commands can be persistently accelerated. While all of this sounds complicated, accelerating a data model is incredibly simple. Select Settings and click on Data Models. The lightning bolt will tell us if a data model is accelerated or not. As you can see, the Linux Server Access data model is not currently accelerated. If it was, the lightning bolt would be lit up. Selecting Edit, we have the option to edit acceleration. Clicking on it, we select the Accelerate checkbox and choose a summary range. We know our users will not need to search more than a few months of data at a time, so we select 3 months. There are some advanced settings options. These should only be used if you are experiencing summary creation issues, so we will leave them alone. Finally, we click Save. We can see that our data model is now accelerated and see details about the acceleration. Now, when we click Pivot, results are returned much quicker than before. Any report saved using the data model will also benefit from the acceleration. Earlier, we talked about the files that are created for data model acceleration. These files are called time series index files, or TSIDX files. While they allow us to accelerate data models, they actually play a big role in Splunk search in general. When data is indexed into Splunk, several files are created in the hot bucket, including raw data files and TSIDX files. TSIDX files include 2 main components, the lexicon and the posting list. The lexicon is an alphanumerically ordered list of terms found in the data at index time. The posting list is an array of pointers that match each term to events in the raw data files. Any fields that are extracted at index time show up as key value pairs in the lexicon. You can think of the TSIDX as a very complex index for a book, where every word included in the book is found in the index. When a search is run, Splunk searches the lexicon inside TSIDX files for the supplied terms. It then uses the pointers to only open and read the raw event data matching the terms, causing your search to be much faster than if it had to search just raw data. This building of TSIDX files also happens when a data model is accelerated, with key value pairs from the model being added to the lexicon. Ad hoc acceleration creates TSIDX files for the data being accessed on the search head while the summary is built. These files will only last while a user is in the pivot editor. When the summary is built for a persistent acceleration, TSIDX files are placed parallel to the buckets that contain the events referenced in the file and which cover the range of time for the summary. These files will be updated every 5 minutes, and outdated files will be removed every 30 minutes.
The data model command allows you to display the structure of data models and search against them. Let's take a closer look at the data model command. Running the data model command without any arguments generates a list of the data models you have access to. The format of the output is JSON, JavaScript Object Notation. If I wish to get information about a specific data model, I can specify the ID of the data model in question as an argument. Let's examine ACC Buttercup Games online sales. The ID is the value seen in the model name field output of the JSON data. Appending the ID value to the command and running the command gives me information specifically about that particular data model. Expanding the object name list element of the JSON output gives me a list of the IDs of the data sets within the data model. I can, from here, determine information about each of these specific data sets. If I wanted to get information about the HTTP request data set, which is data set number 1 in the list, I would come down to the object list here and look at element number 1, and I would be able to get information about HTTP request. On the other hand, if I wanted information about successful request, I would come down to element number 2 and get information about successful request. But there's an alternative. Like with the data model ID, I can also use the dataset ID as an argument. I place the dataset ID after the data model ID, and I get information specific to this dataset. For example, in this case, examining the successful request dataset, I see that it's a child dataset and its parent is HTTP request. If I take a look at the HTTP request dataset, by using its ID as the second argument, I look at its lineage element and I see it just mentions HTTP request. What this indicates is that this is a root dataset. Let's go back to the successful request dataset as our example. The other thing I can do is I can pull data through the data model. And I do that one of two ways. I can use the search option, and what I get is, as a result, a list of events and a populated field sidebar. Take note that using the search command, the fields identified in the field sidebar indicate which data set defined that field. So the action field was actually defined in this data model through the HTTP underbar request root dataset. On the other hand, is not successful remove. That field was actually defined in the dataset successful request, which is a child dataset to HTTP request. As another option, I can use the command flat, in which case the field sidebar does not indicate which dataset defined that particular field. The other thing to note about drawing data through the data model command with either search or flat is that I don't have to specify the name of a dataset. So if I take off the name of this dataset here, successful request, and run my search, I still get event output. Please note, though, that it chose automatically a dataset to use. In this case, it chose HTTP underbar request. Why that dataset? Because that is the first dataset in this data model. If I take off the data model altogether, I get an error. So minimally, when I want to use the data model command to pull data from Splunk, I have to specify the ID of a data model. The other thing to note about IDs is that they are case sensitive. Here, I spelled everything correctly. On the other hand, I've changed the S in sales to be a lowercase s, and when I run this, I get an error. And it's telling me that it can't find a data model with an ID of ACC Buttercup underbar games underbar online underbar lowercase s sales. The final thing I want to talk about when pulling data through the data model command is where that data comes from. As we learned, data models can be accelerated. This is, in fact, an accelerated data model. More than likely, the data is coming from the acceleration summaries, but it doesn't have to. The acceleration summaries for this data model only go back at most probably about 3 months. But there's data in our index that goes farther back in time. So if I run this search over all time, it's taking quite a while. What's going on is some of the data that's qualified by acceleration summaries is being retrieved and accessed just through those acceleration summaries. But for the data that's outside the range of the acceleration summaries, Splunk is going out to the raw data. So we've retrieved 2.4 million events, and it took 16 seconds, 17 seconds to retrieve that data. But I can, with the inclusion of another option called summaries only, and setting this option to true, this will force Splunk to only consider data that's covered by acceleration summaries. Since this is an accelerated data model, it does have acceleration summaries. My search is done. Something to note, though, not as many events. I went from over 1 million events to 456,000 events. And also, the time it took to run the search went from 16 seconds down to 4 seconds. I can run the data model command not only against data models that are accelerated, but also unaccelerated data models. I'm going to do this over a smaller period of time. Buttercup Games Online Sales is an unaccelerated version of the data model I was using before. But likewise, I can tell Splunk to only consider the data covered by acceleration summaries. By using the summaries only equals true option. But this is an unaccelerated version of a data model. What's going to happen? Well, it's very simple. I get no results. I don't get an error. I just don't get any results. It's not syntactically incorrect to use the summaries only option against data models that don't have acceleration summaries. You just won't get any data back. And that is the data model command. So let's review. Running the data model command without any arguments gives you a JSON structured list of the data models that you have access to. It's a generating command, so you need to begin to use it with a leading pipe symbol. Optionally, you can specify the ID of a data model, and it'll retrieve information specific to that particular data model. If you expand the object name list element of the data model, you will get the IDs of the data sets that are defined within that data model. You can get information about each data set by expanding the objects element and querying the corresponding element of the objects list for the particular data set in question. Or as an alternative, you can specify as a second argument the ID of the data set in question. And you can determine a lot about that data set. For example, you can determine its lineage, the fact that it is a child data set and what its parent is, or the fact that it is a root data set. And as we saw, you can actually pull data through the data model command by using either the search command, which will give you a result of events, plus a populated field sidebar that lets you determine where the field was defined, which data set defined that field. On the other hand, if you use the optional command flat as opposed to search, there's no indication in the field sidebar of the lineage of the data set or what data set was used to define that particular field. And as we saw, minimally, you have to specify the ID of a data model to use either search or flat. If you specify the ID of a data model but no data set, the data is retrieved by using the first data set within the data model. And if you don't even specify the ID of the data model, you get an error. And we saw that data model IDs and data set IDs are case sensitive. And then we finally saw that when retrieving data through a data model, Splunk by default will use a combination of summarized and unsummarized data. If there are qualifying acceleration summaries, it will use the acceleration summaries as a source. Otherwise, it will go out to the raw data. The option summaries only forces Splunk to only consider data covered by the acceleration summaries. And as we saw, if you use the summaries only option with true for a data model that doesn't have any acceleration summaries, an unaccelerated data model, you don't get an error, you just simply don't get any results. And that is the data model command. Splunk provides the tstats command for generating statistics from TSIDX files. The tstats command is a generating command that will generate statistics from either indexed fields found in TSIDX files or fields defined in a data model. It requires the use of a statistical function and has a number of additional clauses. When using the tstats command to access indexed data, it's relegated to only using data found in TSIDX files, which means it can only use indexed fields. But this also means the command is very fast. It requires the use of a statistical function. Most of the functions are those that are found in the stats command, but not all stats functions are available to tstats. The from clause is used when you want to access data through a data model, giving the tstats command access to the fields of that data model. Without access to the data model, tstats can only, again, access fields found in the TSIDX files of the main index, that is, just indexed fields. The by clause is used to group the statistics by the values of the specified fields in the by clause. If you are accessing data from a data model, you have the option of using and forcing tstats to use just the acceleration summaries if the data model is an accelerated data model. Specifying summaries only equals true forces the tstats command to only look at data that is covered by the acceleration summaries. Using summaries only equals false allows tstats to actually access data from the raw data. When you use the summaries only option and you're accessing a data model that's not accelerated, then you get no results. When you use a data model and wish to access the fields of that data model, you have to prefix the name of the field with the data set that the field was defined in. You also have the ability to specify as part of the from syntax the data set in question, but there are certain rules about that data set. First off, it has to be a root data set. And if your data model has a multiple root data sets, it's a best practice to always specifically identify both in the from clause and in other accesses to those fields the data set the field came from. So let's take a look at using the tstats command. Let me demonstrate the use of the tstats command by comparing it with a non-tstats version of a search. I'm going to set my time frame to all time. So this command, index equals star stats count by index across all time, will give me the names of the indexes I have access to that have data. And as you can see, it's taking quite a while to run. And that's because this is looking at the raw event data, extracting fields, and processing and calculating these statistics. Let's take a look at the same command as a tstats command. And as you can see, it comes back quite a bit faster. Let's take a look at the two commands together. I'm going to go up to the activity monitor, go into jobs. Here's the tstats version of this command. And I see the regular stats version. If we took a look at the stats version, this took 18 seconds to run. But if we actually go out and take a look at the tstats version, it took 0.299 seconds to run. Why the speed difference? The reason is the tstats command was not looking at the raw data. It was only looking at fields that are available in the TSIDX file of the index. What this means, though, is that I cannot use tstats for every equivalent stats command. So here we have an example. I'm counting events by action in the web index over the last 24 hours, and I get results. Trying to convert this into a tstats, however, is not going to work. I get no results. And the reason is because action is a search time field. It is not an indexed field. So out of the box, fields such as host, source, and source type are your only indexed fields. But this doesn't mean that tstats cannot use fields such as action, price, or any other search time fields. If those fields are defined as part of a data model, then the tstats command can do statistical processing against those fields. So, for example, tstats sum price from data model equals Buttercup Games online sales by product name over the last 24 hours. And I run it and I get no results. But I just said that if I'm accessing a data model, I should be able to access the fields of that data model. Yes, but I need to understand the data set in the data model that brought that field into existence. In this case, the price field is actually defined in a data set in this data model called HTTP request. And so I must specify HTTP under our request.price. And I need to specify in the by clause the name of the data set within the model that brought that field into existence. I can also specify as part of the from clause the data set in question. The reason we allow this is because a data model could have many, many data sets. But there's a restriction. When you specify the name of the data set in the from clause, it has to be a root data set. Attempting to specify a non-root data set will generate a syntax error. Successful request happens to be a child data set of HTTP request. Even using the prefix of the root data set to successful request still generates a syntax error. But when I specify the name of a root data set, I have no problems. Let's investigate this further by looking at another data model that happens to have multiple root data sets. So we have a data model called vSales. And it has a number of fields, but it also has a number of data sets. In this case, notice my syntax. tstats sum us.price from data model vSales by us.product name. I am not mentioning in my data model command the name of the data set. I am mentioning the data set as part of the field specification. Let's try using another data set within this model. Let's try, for example, the Canadian data set. And when I specify the Canadian data set as part of the field specifier in this tstats command, I get no results. And that's because the name of the data sets for the field specifications doesn't match the name of the data set that we're actually accessing in this data model. And that's because when I don't specify the name of a root data set as part of the data model specification in the from clause, it defaults to the first data set in that model. To do this properly, I really should be putting the name of the data set as part of that from clause. There's some other interesting features. If the field is specified as one of the classic indexed fields, like host, source, and source type, I am not required to prefix that with the name of the data set. So it's perfectly fine to use by source. Now, in this case, there's only one source. But since source is an indexed field found in a major TSIDX file, it doesn't need to be prefixed by the name of the data set. The same thing for time. Time is actually very interesting. If I group by time, I get behavior very similar to a command called time chart. In this case, I'm seeing things broken down to essentially 30-minute intervals. Let's do a count. On the other hand, if I actually go out and specify over, let's say, a 7-day period, I'm getting daily intervals. The behavior of using tstats grouping by time is very similar to time chart. And likewise, I have the ability to use the span operator. So instead of giving me daily items, I'm getting 12-hour periods. When I access data through a data model, pardon me, got to get the name of the data model correct. When I access tstats using a data model, I have the ability to use data models that are accelerated or unaccelerated. In the case of an accelerated data model, if there are acceleration summaries, they'll be used, or they can be used. I, in fact, can force the use of only acceleration summaries using the tstats command against a data model that is accelerated by using the summaries only option. Or I can use it false. Let's take a look at the effect of this a little bit more closely. I'm going to change my time range. We'll go back 10 hours, snapping to the hour, and I will choose 1 hour, snapping to the hour. Benign space be 120, and we see that the job, without forcing the use of acceleration summaries, took 0.36 seconds. Specifying true seemed to go a little faster. 0.09, actually many orders of magnitude faster. However, there can be some disparities. I'm going to run this search across all time with summaries only equal to true. And I'm getting over 400,000 events. But specifying false and I'm getting over 2 million events. Why the difference? Well, with the case where I've specified summaries only false, it is accessing the summaries, but it's also going outside of that and going to the raw data. Whereas when I specify summaries only equals true, it's only relegated to only the data covered by the acceleration summaries. I also have the ability to do such things against an unaccelerated data model. Where I get over 2 million events returned. But in this case, when I tell the command to force it to use acceleration summaries exclusively, since this is an unaccelerated data model, it comes back with no results. So let's recap what we've covered so far. We've seen that the tstats command can work with and without data models. When you use tstats without the benefit of a data model, you're relegated to just using fields that are specified in the TSIDX files of the index, that is index fields. On the other hand, when you specify a data model, you have access to the fields of that data model, but you have to prefix those fields with their data sets. You can use them in the by clause. Though I didn't demonstrate it, you have the ability to go out and use it in the where clause. So we saw that we can use tstats to search both accelerated and unaccelerated data models, but there's a performance gain to using tstats with accelerated data models. We saw that if we group our statistics by time, tstats behaves like the time chart command. If I don't specify a range, tstats will dynamically, like time chart, choose a dynamic time span. 5-minute time range would be 5-second time spans, whereas a 24-hour time range we saw was a 30-minute time span, and a 7-day time range produced a 1-day time span. But as I demonstrated, you can overwrite that with the span option. Another thing to note that's a difference between stats and tstats is that I can only use wildcards for field values. The stats command allows me to use wildcards in various parts of the syntax where I specify a wildcarded field name. Wildcarded field names are absolutely not allowed in this tstats command. When you're running searches that are accessing just indexed fields and you're using the stats command, think about doing a tstats instead. The performance benefits can be phenomenal. So in each of these cases, we have a regular stats version of a search and its tstats version. And as you can see, 0.08 seconds for the tstats version, 1.59 seconds for the stats version. The performance gains are very significant. Because of this, there are going to be certain syntaxes in SPL that Splunk will attempt to convert to a tstats. For example, if you are using the data model command and piping that through a stats command, Splunk will actually convert that and run the tstats version of that command. There is also a similar option available for simple stats to tstats, but this optimization is not on by default. It's actually turned off, but you can go ahead and turn it on, or I should say your administrator can enable this particular optimization. The reason this optimization is not turned on by default is that it has a negative effect on something called summary indexing. And when you install Splunk for the first time, we don't know if that site is going to be using summary indexing or not. As such, we have this stats to tstats optimization disabled out of the box. If you are not going to be using summary indexing, then you might think about enabling this particular optimization. Both of these optimizations are enabled in a configuration file called limits.conf.